Can you hear me?
Yes.
Okay, so I'm going to talk about detector simulation requirements from HEP experiments. And first of all, I'd like to thank the organizer for this invitation to give this talk. And secondly, if I manage to switch my slides, I'd like to thank all the people who kindly contributed to these slides, sending them their inputs and feedbacks, basically from all the major HEP experiments. So let's start with CPU requirements for detector simulation. As you may know, detector simulation is one of the largest consumers of LHC computing resources, and it accounts for a very large fraction of the computing needs for every experiment. If we look at the run-tree needs, already LHCb and LHC experiment will start to see a major change in their workflows, because, for example, LHCb already will process more than 40 times the number of collisions that it does today, and LHC will read out collisions at a rate of 50 kilohertz. So basically, as a consequence of this increased luminosity and also interaction rate, a significantly larger amount of data will have to be collected, but also processed. So for example, Alice experiment estimates that the simulation requirements will increase by a factor of 20 in their case. So simulation is clearly the leading CPU consumer for both experiments. And you can see here, for example, projections for the future of the LHCb experiment, where you can see that simulation will lead the CPU time also in the future. Here you can see a projection of the computing needs of the experiment for the next 5 years, and the green bars are basically referring to what will be the computing needs of the experiment if it will decide to produce their Monte Carlo samples fully with 100% detailed simulation. The blue line is referring to the baseline, while the red line is referring to what are the available resources to the experiment, considering also the opportunistic resources. So it's clear that, for example, in the case of LHCb, if they want to stay within the pledged resources, they can do that only adopting a very aggressive fast simulation model, which is represented by this dashed line here. Let's see how we'll do also Atlas and CMS experiments. For them, the major game change will happen in run 4, so with the high Lumi phase. In fact, there the beam intensity will rise substantially, and that will basically imply that the pileup will increase by a factor of around 35 today to 200. And accurate simulations will be needed in order to meet the desired physics precision, but at the same time, larger Monte Carlo samples will be needed if the experiments want to avoid that the simulation dominates the systematic uncertainties. So Atlas experiment, for example, is planning to different R&D lines in order to meet the computing needs for the future. And in this plot, you can see basically a projection of the computing needs for the next 14 years, where the solid black lines are representing a projection of the computing availability, considering to have a plus 10% or a plus 20% per year of the budget. And if you look at the circle, the line with the circles, you can see a projection of what will be the computing needs if the experiment will keep the same computing model as in run 2. And it's clearly way off the availability, basically. Instead, if you look at the triangles lines, they are referring to projections related to the two different R&D lines. The one which is called the conservative R&Ds, and the other one is an aggressive one. So you can clearly see how important it is for the experiment to be successful in these R&Ds activities. Similarly, for CMS, we see here a plot which is showing the projections of needs of the experiments for the next 10 years. And here you see the projection of the availability of computing budget, while the blue lines are showing us what will be the computing needs if under two different scenarios. One, where the pileup values are different, the integrated luminosity and also the data data taking rate is different, if the experiment will not put in place any R&D. So this is what would happen without any significant effort from the experiment. So it's clear that there is a lot of effort which both experiments are pushing towards R&Ds. What should be said also for CMS is that differently from the other experiments, the last CMS projections pointed out that reconstruction will be the major computing power consumer. So a very big effort is spent in the experiment towards reducing this time needed by reconstruction. And in this scenario, of course, simulation and other components will become more and more important. So any effort towards speeding up simulation, of course, is of utmost importance for the experiment. Here in this slide, you can see different sketch of the simulation frameworks implemented by the different HEP experiments. And there is one thing in common between all of them, that is Gen 4. So Gen 4 is at the core of almost all HEP experiments, simulation infrastructures, except for Alice, that actually provides the possibility to use different simulation engines, not only Gen 4, but also Fluka and Gen 3. And anyway, all of the 4 different simulation frameworks provide the possibility to mix what we call full simulation, that is basically the full detailed Gen 4 simulation, together with the fast simulation options that can be available in the different experiments. And that can be done either using the Gen 4 FastSim MOOCs or, for example, as it's done in Atlas, through a different framework, in this case, the integrated simulation framework. So given this context of that I described of high need and shortage of CPU power, there are a lot of R&Ds activities ongoing in each experiment, and we can group them and organize them along 3 different major lines, if we can say so. The first one is concentrated on the efficient use of parallel computing architectures. The second one is based on GPU based HPC exploitation, and the third one is, of course, fast simulation. So I will touch briefly all of these 3 points before moving to detailed and experiment-specific requirements. So let's start with the computationally efficient use of modern computing architecture. This is very much important for every experiment because they are pointing on fast simulation, but of course full simulation is still needed. And in this respect, Gen 4 we know offers a multi-threading capability since version 10, since many years. And there has been in the recent years an heavy effort to migrate to a multi-threaded paradigm and optimize this kind of workflow in each experiment. So we will see for run 3, for example, that LHCb will use this new Gaussian-Gaussino system, and here you can see some nice results about throughput and scaling. Atlas will use Athena-MT, and here you can see some nice plot about scaling in throughput, but mostly about gain in terms of memory footprint with comparison with a multi-process paradigm. And Alice, for example, is working on the O2 plus VMC system that will provide the multi-threaded capability thanks to Gen 4, that it's the only engine which is actually supporting a multi-threaded capability. So Gen 4 will become more and more important also for the Alice experiment. In CMS, all the workflows are running in empty mode since run to start, but they are pushing a lot of effort actually to make all these workflows much more efficient since then. About GPUs, as it was already said, and it's clear to everyone, GPUs are currently one of the main challenges for the exploitation of HPC centers. In fact, the new trend is to provide more and more fraction of computing power in HPC systems through GPUs. So all HEP experiments have been actively working in the last few years in this respect in order to try to re-engineer their software workflows in order to be able to run on GPUs. For what concerns simulation, we have to, for the detailed Monte Carlo simulation, we know that Gen 4 cannot currently exploit GPUs, we hoped it will be able to do that in the near future. And we know that there is actually an heavy R&D ongoing with many interesting projects in this respect. And there is also a big interest and a big effort in the community in this respect with some other projects that we will hear about actually during this session. For what concerns fast detector simulation, there is also R&D ongoing within the experiments. For example, to try to port the fast simulation like parameterized calorimeter responses on GPUs with, for example, fast CalOSIM GPU project, or also, of course, using profiting from GPUs for machine learning, for example, to do network trainings or hyperparameter optimizations. But that, of course, it's only a small fraction of what will be desirable to have available. Just few words about fast simulation. I will not spend much time here because the next talk will be about machine learning. So Kevin will talk more in details about that. But I wanted to put these slides here just to say that all the experiments are pushing a lot of effort in this respect for fast simulation techniques and machine learning. For example, Atlas is designing a new fast calorimeter simulation that will be an hybrid that will mix the parameterized calorimeter simulation together with a GAN approach that will be used for high energy hadrons. And it's also working on a fast chain project that will give the possibility to mix, according to the needs, fast simulation together with fast digitization and fast reconstruction. Similarly, LHC Experiment is pushing lots of research in machine learning, trying, for example, to simulate TPC clusters using GANs. Very active in this respect is also the LHCb collaboration with development of calorimeter shower simulation, shower libraries that are specifically point libraries. They are also developing GANs for PIDs and are also exploiting the use of variational autoencoders. And they are also working on this new Lamar approach, which will be a combination between parametric and machine learning techniques. CMS has already since round 2 put in place a fast processing chain for simulation and reconstruction, which has been used for 10% of the total production of samples. In fact, their full simulation together with reconstruction was actually fast enough for their needs up to round 2. But that scenario will change with round 3, 4, and 5. So they are actually pushing efforts also in this respect in order to improve and validate new way of using fast chain according to the needs of the different analysis groups. Okay, now about experiment-specific simulation requirements, starting with the LHCb experiment. So here in this plot, you can see a very nice detailed view of the Gen4 timing test within the LHCb detector. And here you can see what fraction of time is actually spent on each subdetector in order to understand where to focus the attention. So for the LHCb experiment, for example, one of the major hotspots are the RIC calorimeters and also the calo. So the RIC detectors, sorry, for optical photons and the calorimeters. So for them, any improvement coming from Gen4 that can speed up the code base will be actually very much important. They are also approaching new and complex fast simulation techniques, so they would like to and appreciate from the Gen4 collaboration a continuing support in this respect. And a very big focus for the experiment, as said, it's RGPUs, because they will likely use and have access to GPUs at the HLT farm for the next runs. So for them, it's very much important to be able to use and exploit those resources properly. Also, the experiment is very much interested in exploiting opportunistic resources, and there has been some study ongoing with the multiprocessor version of Gauss that was tested at Cineca in Italy, and they will eventually use Gauss on Gaussino multi-threaded infrastructure on HPCs. And at the same time, they are also having a look at GPUs with some preliminary R&D that could, so they would like, for example, to see and use optics for ray tracing of optical photons for their rig simulation, which is, as I said, a major hotspot for the experiment. Moving to ALICE, as said, also the ALICE experiment will actually face big challenges in run 3 and run 4, with the simulation requirements increasing by a factor of 20. So for them, it's also very much important to be able to exploit all of the computing and opportunistic resources available on the grid. So in this scenario, for them, a requirement will be to have a faster simulation toolkit that could, in principle, increase the event rate substantially, also allow to make good use of novel hardware. And at the same time, it's important to continue to improve the speed on ordinary hardware. So for example, with the integration of WebGeom that is planned, novel steppers which are being developed, and some other very interesting and ongoing development. A second point will be to have a more flexible data handling, and that was already mentioned by Mark. So have a less centric approach based on an event, and give the possibility, for example, to have a parallelization at the sub-event level for big events. And at the same time, for example, allow to treat groups of events in one chunk if you have, for example, very small events. So you want to treat them all together, so to give this possibility. Furthermore, another requirement will be to have more tools around simulation, tools that could help, for example, experiment-specific tuning according to, for example, all the possible geometry optimizations, all the possible physics cut optimizations, geometry cut optimization, or tuning of parameters, for example, selection of the best stepper parameter. So the idea would be to have the availability of tools that could help developers to tune their simulation according to the specific need of the detectors in an easier way, basically more automatic. CMS, in the same line with the other experiments, it's very much focused on the use of GPUs and CPUs, mainly GPUs for the HLT farm. So for them, in this context, also will be very useful to have more infrastructure for plugging classical and machine learning fast sim techniques. For what concerns for simulation, it will be very much needed for round 3 and also phase 2. And actually for phase 2, they expect that their full simulation will be between 1.5 and 3 times slower than in round 3. So any CPU optimization will be vital for the CMS experiment, as for also the other experiments. And they would like to have a quantitative estimation of what's foreseen for the next years. Another requirement is about trendy friendliness to be improved. For example, trying to remove all serialization points as much as possible, to reduce the startup time whenever possible, and be able to customize and configure in a customized way as much as possible GM4 functionalities in order not to use all these functionalities which are not needed by the experiment. Also, CMS traditionally integrates early new versions of Gen4, and they managed last week to integrate in their simulation infrastructure Gen4 10.7 plus the GEOM, and they plan to use it for Run 3. They report to have had a very successful experience also with the Gen3 prototype, even though it cannot be used in production, but it was useful for the experiment to draw a technical path for integration, so that basically their infrastructure is now ready to basically integrate any new coming simulation prototype. And the experiment will continue to explore, of course, experiment-specific optimization, and also adopt new optimization from the Gen4 team. And a very big interest was expressed in the forthcoming WebGeom navigator.
Can you speed up a bit?
Yeah, I have a few slides left. Now, Atlas, in the Atlas experiments, there is a very active Gen4 full simulation optimization work, which is ongoing. And the experiment is taking advantage of all the intrinsic performance optimizations which are coming with newer Gen4 versions. There has been some very nice speed up confirmed thanks to the recent EM physics development and optimization. Also, they are working on optimization with tuning of G4 parameters, on neutron, photon, Russian roulette, EM range cuts, some nice geometry optimization related to the EMEC, and there is also a nice machine learning R&D ongoing about guided steppers in geometry, and another work done on the magnetic field tailored switch off. Also, the experiment is converging on the static linking of Gen4 that will be included in Run 3. And one requirement is to explore actually machine learning options, especially for simulation optimization. So it would be good to have an interesting, at least to try out and explore the possibility to have machine learning solutions to optimize the detector simulation and optimally reweight or retune all the parameters which are basically available from Gen4. The experiment is very much into R&D effort for fast simulation, but the full simulation will be, of course, important. So any speed up in simulation for Run 3 and 4 is also for Atlas very much important. There is a big interest in all the Gen4 optimization, the VecGem Navigator plugin. We are testing new steppers. And another requirement is about better support of predefined decays for quasi-stable particles. Again, I want to stress this point of how important it is to use GPUs and accelerators also for Atlas. And another request is to make each component of the detector simulation as independent as possible so that it will be easier to mix fast and full simulation approach. And also another requirement is about exploring machine learning options for fast simulation, for example, for hadrons simulation like this plan, this R&D, which is ongoing in Atlas. So this brings me to my conclusions, and here in the last slides I wanted to collect all the common highlights from the different experiments, which are clearly, first of all, the interest in heterogeneous hardware. So any R&D or work ongoing in this respect is very much important and very much needed from the experiment. Second, a very big enthusiasm about any R&D activity that can address the shortage in CPU power. So all the memory optimization improvements, CPU improvements are very much important and appreciated by every experiment. Third is the extended support for these different fast simulation options. So for example, developing a common framework for fast tuning, validating and optimizing the simulation will be very, very interesting. And finally, the development of machine learning tools that can be used and shared among experiments, for example, to model and optimize the modeling of complex detectors. And that's it. Yeah, that's my last slide. So thank you for your attention, and I'm happy to answer any question.
Thank you, Marilena, for the very nice and comprehensive overview. So we can take a question now.
Yes, I don't see any hands raised.
Yes, may I do just one comment?
Sure, yeah.
This is an announcement. I would like to inform that people listening to this talk that Marilena has agreed recently to become the new chair of the technical forum of Gen4. So she's a good person to who you may do requests for whatever thing which is concerning simulation.
Thank you for proposing it.
Congratulations, Marilena.
Oh, thank you.
There's one question in Google Notes by Gloria. Would you like to ask it?
Yeah, you have shown that there is a lot of activities that is started or is starting in the experiments, and Mark showed it on Gen4. How do the experiments see collaboration on this between themselves and Gen4 on the various topics of R&D?
Yeah, so there are, I think there are multiple official occasions where already the experiments and the Gen4 collaboration are exchanging and their work and also communicating, like as the Gen4 technical forum that was mentioned by Mark. And so that's a very good occasion to strengthen this kind of collaboration, or also the recent LPCC workshop, or next year there will be one dedicated workshop about fast simulation. So these occasions are, in my opinion, very important to enforce and empower the communication between experiments and Gen4. But at the same time, I would see that since some of the topics are really very much important for every experiment, maybe one could, with the help of the HSF community, for example, try to have a forum that could be not only just an occasion of exchanging different R&Ds from different experiments, but I think it would be fantastic to have the possibility actually to work together in order to have very much specific direction to follow, and also requirements and needs. I don't know if that's very much too much ideal, or if that's possible, but what would be good, I think it would be to have, if the experiment as well as Gen4 managed to attract new people in the collaborations that are committed to a specific project, why not? We could start to envisage some kind of more strict collaboration on specific topic between the different collaborations. I don't know, this is my maybe idealistic view of what could be done.
But I like it.
Okay, I don't see any other hands raised, and I guess we don't have.
Peter, could I ask a quick question? Sorry, I can't raise my hand because I'm a co-host, you know, this stupid thing about Zoom.
Okay.
And I think it's more of a question actually to Mark and Alberto. So given the requirements that Marilena has put forward from high energy physics, how do you see that they fit with requirements from other user communities? And is there a possibility of collaboration with other communities who are interested in similar topics?
For sure, the request on computing speed and porting to GPU is by far the strongest demand of the LHC community. For sure, any community would like Gen4 to be much faster, but for the main one, which is the major speed up, the strongest pressure comes from the LHC community. And other requests, I would say, we don't have that level of strong requests from other experiments. Maybe some from the nuclear community, but really the strongest pressure comes from the LHC community.
Okay, we have Paolo who has raised his hand.
Yes. Hi, Marilena. Nice talk. I was wondering if the GERN, given all these initiatives, optics, Excalibur, Celeritas, the various machine learning projects, I was wondering if the GERN4 community, and more broadly the simulation community, is thinking about capturing some of the more technical parts of your requirements into benchmarks. You know, essentially geometries, data sets, and plots that can be shared and used by other people as a way to check whether what they're doing makes sense or is it up to spec.
Yeah, this is something, of course, that is doable and actually desirable. I think in order to, like Mark was showing, for example, in his slides before, it's important to understand what portion of our problem is actually parallelizable and where we should focus our attention. So I think a joint effort between Gen4 and experiments in this sense is very much desirable.
And just to have a few words, to add a few words, there is this, we have this John Ford R&D task force, which is ongoing and which is well aware of these developments. And so this is a way to strengthen communication between users in John Ford.
Okay, I don't think we have more questions.